Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour.
Hello, and welcome to another episode of On Air Actually Rocket Science, the Student Council of Aerospace and Geodesy's official podcast. I'm your host, Killian, and joining us is Paula. And today we're happy to be joined by Professor Markus Ryll, who is the head of the chair of Autonomous Aerial Systems at the Technical University. Thank you very much. Thanks for joining us. We're just going to start with a few this or that questions, just to gauge who you are a bit.
Perfect. Thank you. Thanks for being here today.
Thank you for being here. Okay, so the first one. Would you prefer a drone that looks like a bird or a UFO?
Oh, then I would choose the bird.
Ooh. Remote control or autonomous flight?
Oh, there it's clear, autonomous.
Coffee or tea?
Coffee.
Ordering food or eating out?
Eating out.
GPS-based or visual-based navigation systems?
Visual-based navigation.
before you finish it. A vacation in the mountain or a vacation at the seaside?
That is a bit tricky. I know I have to choose one, but I can explain my decision maybe afterwards.
Go ahead.
So I would choose probably the mountains.
Okay.
I enjoy both, but I think there's just more to do in the mountains than on the beach side.
Okay, that's fair. All right, so let's dive right in. Could you maybe just start by introducing yourself, your career starting after high school, your education and where you went with that sense?
Okay, let's start maybe now and then go backwards in history. So I am now since 2.5 years or almost 3 years here at Professor at TUM, mainly working on autonomous aerial systems. And before that, I was for 3 years at MIT, a postdoc there in Boston, Massachusetts, and then as well, they were working mainly on autonomy for aerial systems. Before that, I was a postdoc for 3 years at La CNRS, which is a research facility similar to Max Planck Society in Germany, located in Toulouse, France. And before that, I did my PhD at the Max Planck Institute for Biological Cybernetics in Tübingen, and there I was for 4 years.
But before the PhD, your master's degree was?
Yes, I did a master's degree in medical engineering, actually. So I did my PhD in control theory, but I did my master's degree in medical engineering. Maybe a little bit of background. So I did first a diploma in mechatronics, and then I thought mechatronics was a bit dry.
Okay.
And I decided to do an additional master in medical engineering, which is very similar to mechatronics, but it has this additional add of the human factor inside.
So I guess you'd say the motivating factor behind going into medical engineering was more the human factor, but
yes, exactly.
So you know, for people who maybe don't know, what exactly do you understand by medical engineering? And
I see. So basically, think about systems in general that are somehow related to the healthcare domain. That can, for example, be a pacemaker, that can be an fMRI tool, that can be something for an operation. So all these kind of systems that are well known or well studied, usually using mechatronics. But then as well, it includes the human factor. So you have to as well understand how does the human body work, how does the human body react to certain things. You have to understand tissue of humans. You have to have some background in medical or diseases and this kind of stuff. So I just choose this as this was at that time for me, really interesting. I considered to work in the field of medical engineering. But then afterwards, I decided that robots are a bit cooler or easier. Maybe let's say easier.
Do you see any connection between the field of medical engineering and what you work on now? Like, do you draw anything from it?
So I definitely learned a lot about the human body and so on. But these are parts that I'm currently not using anymore. But please keep in mind that medical engineering is probably 85% mechatronics and 15% related stuff that is more related to human healthcare.
And so do you think it was hard to, I mean, those 15% that I guess you hadn't done medical school or anything in that, was that a challenge switching over and having to adapt to that?
I wouldn't call it a challenge. So in order to do a master's in medical engineering, you have to hold a bachelor in medical engineering, or you have to retake some courses. And I just decided to retake some courses as I didn't have a bachelor in medical engineering. And that was actually really a nice benefit. So I really enjoyed these classes. So that's something I for sure do not regret doing.
And besides it being easier, what led you towards drones and autonomous systems?
So I was actually, to be honest, always curious about robots. So since I was a kid, I really enjoyed playing with robots. I had this, I don't know whether you know them. So there are, in Germany, there's very famous, there are this Cosmos Experimentierkästen, so some kind of experimental toys for kids where you can play around, and I always loved this electronics and so on. And just really from an early childhood, that was something that was fascinating me. Working with robots is very satisfying because you create something and you see that you can make some progress. You see that you can achieve things. So the reward is quicker than in many other disciplines. And I think, to be honest, really, if you take a look to robotic scientists, I don't want to judge it on other fields, but these are usually people that are highly engaged. They work really a lot. But at the same time, I tend to feel that these are as well the most happy people because they really create something and they see urgent or immediate reward from their work. So that's probably one of the decisions or reasons why I decided to work on robots.
That's really interesting. Well, we've kind of went already into the topic of drones. Before we really start, can you kind of explain what you understand under a drone?
So if we think about the definition of drones, drones are unmanned aerial vehicles, and that can include a lot of things, right? So unmanned aerial vehicles is really a broad field, starting from the small-scale quadrotors that we see here on the desk, or that everybody has at home. You know, you can buy a drone for like $50 by now in the local supermarket. But then there are larger systems. There are rotary wing systems, as we see them here. There are fixed wing systems, so, up to a huge scale, right? There are like this military Reaper drones and so on that are really very big unmanned systems. In my research, we only focus on civil applications. And mainly on smaller systems. But for example, we have a collaboration with the company Volocopter, where we as well develop control algorithms for larger scale drones.
Okay, so you know, you mentioned before that there's a quadcopter sitting in front of us. You mainly focus on quadcopters in your research, do you? But what about especially that configuration makes it attractive for your research?
Maybe let's do one step back.
Go ahead.
I personally prefer the term quadrotor.
Quadrotor.
So not quadcopter. Let me explain you why. That's a bit of an interesting thing. So the term quadcopter, right, is something that is related to helicopter.
Right.
And that's where it comes from. But to be honest, it is a wrong use of words there. Why is this the case? So a helicopter is a Greek word. It's actually a helic, which is like cyclic, and opter is a wing. So the correct word is actually a helicopter. And in German, we made helicopter out of it. And then basically helic doesn't mean anything anymore.
Right.
And so therefore, I prefer the word quadrotor, which is maybe not as well the best word, but at least it means four things that are rotating.
Right, okay.
So therefore, I use mainly the word quadrotor for that. Why do I use quadrotor? So when I started my PhD, this was a rather new technology. I started my PhD like 12 years ago. And at that time, already still like flying was still a bit of a challenge. Now this technology is very mature, right? We know how to fly, that everybody can fly it at home. There are plenty of controllers. Every hobbyist is able to build a quadrotor. But it's still it now became an easy to use tool that you can handle well, but still do interesting research on it. So that's a platform that is easy to use in the lab. You just need one student, or one student can individually work on it. For example, if you compare that to other research domains, that's like in the field of robotics, that can include like humanoids or autonomous cars, right? They're like really big and chunky machines. and you need a huge group, just first of all to maintain the software stack, but as well to do experiments with that. Using Quadrotors has really the benefit that an individual student can directly make experiments and still be at the edge of technology and academic research.
And so, what about compared to other configurations of drones? What about the Quadrotor itself makes it more attractive for your research than other configurations?
So one of the benefits and why I think Quadrotors are well used is, first of all, again, the mechanics are simple, right? So, for example, if you compare that with a helicopter that has like a swash plate, which includes or challenges the mechanical parts, a Quadrotor is simple to use. But the benefit of like a Quadrotor compared, for example, to a fixed wing body system is that you can as well navigate it in a narrow field, right? It can just hover in place, and you can easily, first of all, use it in the lab, but at the same time you can do experiments that you can't do on a fixed wing system, right? So you can do navigation in very confined spaces. You can use a Quadrotor to, for example, fly through a very rumbled environment that is full of obstacles, really challenge the perception system, challenge the control system, things that are significantly harder to do with a fixed wing system. So with a fixed wing system, right, you already have like a certain velocity. And if you want to then do, for example, navigate to very confined space and you do a tiny mistakes, then you completely destroy your vehicle. I mean, we are crashing our vehicles regularly. So that's something that we're very well experienced with. And PhD students struggle with that because usually one failure means at least 1 or 2 days of work to repair everything, but you don't completely destroy your system. And therefore, it is as well a very useful educative platform.
Is there any particularly impressive crash you remember?
Oh, plenty. So most crashes appear in edge cases that you do not foresee, right? This can be either due to some kind of a mechanical failure where you didn't pay enough attention, or another option is that something in your control algorithm worked completely different than you expected. Maybe let me tell you 3 different things that happened. So let's start with the oldest. So during my PhD, we built from scratch a completely new octocopter. So with 8 rotors, it was a pretty beefy and big machine. We just assembled it and flew it together with a remote control. And as we assembled it together without paying attention to any safety mechanisms, and we just flew it the first time with a remote control, we didn't pay attention to that there might be the end of line of our remote control. And we just flew it out of sight of the remote control, and it just started because we didn't implement any safety mechanism. It just drifted away forever. And so this was really a completely new machine. Costed, I think at that time, like 3,000 euros, so which was for me as a PhD student a lot of money. Of course, I didn't pay it, but my lab paid it. But then I had to go to my supervisor and tell him, yeah, we just lost it.
What do you mean you lost it?
It just drifted away, and we knew it somewhere went down in a forest, but we never found it back. So it was gone forever. And we even went around and left posters. Whoever found it should bring it back, but it didn't help. So this was one failure. Maybe another, a simple failure that happened is, or that's something that can happen easily, just during a high-speed flight, one of the motors went off. So we didn't tighten the screws fine enough, and just the motor went off. And that just resulted at a speed of 30 kilometers per hour in a looping that then crashed directly into the ground and completely destroyed the drone. So this is the mechanical failure. But of course, as well, this may be more interesting is actually we have lots of edge cases where, for example, the perception goes down. So one of another field experiment, we were flying an autonomous drone around houses, and suddenly the vehicle flew around a corner and faced the sun. And the visual system didn't react fast enough, and so we didn't see properly enough the corner of the house and just crashed into the corner of the house. And so these are all the challenges that you see. So you have challenges in all kind of levels. So mechanical failures, configurations that you did not foresee, perception problems, control errors. And so as well, one thing you try, or how you try to avoid the crashes, is that you simulate the drone. So you try to find these edge cases in simulation, but of course you can't find all edge cases.
obviously drones is a topic that encompasses many parts of, let's say, the aerospace degree that we're doing. How much interaction do you have between other chairs when researching? For example, I'm thinking aerodynamics or control engineering.
Just from the topic that we work on, my chair is the closest to Sophia Armanini's chair. And as well, we are having just our office next to each other. So basically, we speak about our research and our problems a couple of times per week. So this is really a very, very close collaboration. In the past, we as well had interesting meetings, especially with the PhD students of other chairs, for example, of the helicopter technology. Because my chair is coming from a robotics background, right? So that is the thing that we know. We know a lot about how to control a system, how to do perception, how to do planning, and everything related to the domain of robotics. On the other hand, here at our department, we're having lots of professors that have a more background really in the aerospace domain. And that is something, of course, where we are lacking knowledge. So, for example, to better understand and to better model the aerodynamics that are happening in the downstream of a propeller, that is something where we can actually learn a lot from other chairs, and where we just realized how much we don't know and how much we didn't understand before we talked to them, and how hard their problems are. So just to give you an example, we just went to the chair of helicopter technology and asked them what are the best models to model the aerodynamics and the turbulences underneath the propeller, because we wanted to build a controller that works in real time, including the aerodynamic disturbances. And they just told us, forget it.
Really?
So that's something you can't do in real time. We have our models, right, that work well, but these are models that we use hours to compute time to then understand afterwards, like a perception horizon of a few seconds. And that is something we had to just first learn to understand that these things are challenging, and there's not an immediate answer to do that.
Can you maybe tell us a bit about your research process? Do you have like a certain steps you follow or something like that?
That a little bit depends on what we're currently doing. So maybe I can quickly summarize what we're in general doing at my chair. So we're having three main streams or main lines of research. So the first one is just like focusing on the autonomy of autonomous vehicles. The second line is towards using aerial systems for aerial manipulation. So where we equip our flying drones with manipulators to grasp objects, to transport objects, or as well to just like really manipulate, to repair things, to place sensors on objects and so on. And the last line of research is how can we apply the knowledge of the first fields to the public airspace. And that is really as well a very interesting transition, because what we can do on these research platforms, right, is we have all the freedom to use control algorithms that we want to use. We can use deep neural networks. We don't have to think about safety and so on. But if we want to use these algorithms in the public airspace, right, then we have to think about certification and all these problems that appear from that. So it is interesting to see there that basically like the public airspace or all control algorithms that run on systems that are used to transport people, right? They are like in the technology level far behind what we're able to do in research. But this makes sense, right? Because we want to be sure that our algorithms never fail. We don't want to have that a plane is crashing or an autonomous drone is crashing to the ground and might even like kill someone on the ground. So having said that, in general, right, we start with the problem. We try to rigorously think about the problem. What is the fundamental problem behind that, what we want to solve? So usually it starts with some problem that we see in our research. So we want to solve a certain task, but then we try to abstract and understand better what is the underlying real problem. And we try to formulate that into some kind of a research question. So that's basically as well the guideline that I tell all my PhD students. So when you think about a problem, try to split it up into an X, Y, and Z problem. So X is, what do I want to do? Then Y is it actually hard? Why hasn't it been done in the past before? Or what is the challenging part that we don't understand yet? And then the Z is, how do you tackle the problem? So what is your idea, your magical trick to solve a problem that has not been done in the past or was not able to be solved in the past? So that's usually the guideline that we use to tackle our research in a group.
And so you already touched on this before, but certifications and just things that we have to deal with as aerospace engineers in the public domain. I'm just wondering, when we're talking about risk assessment, I'm looking at the drone right now, and if one of the rotors fail, is that crucial? So how much redundancy can you actually build into a drone in that sense?
That's a very good question. Again, lots of things can fail on a drone, right? So let's start with the most simple thing. Let's assume now one of the propeller fails. For a quadrotor, as we see it here, in principle, it can still fly. But that's something I have to say in principle. Why is this the case? So we can design control algorithms that will still keep the drone in air. But let's maybe go a step back. So let's explain what is happening there. So on a standard quadrotor drone, right, you're having 4 propellers. And that is great. It means we're having 4 control inputs because we can control the 4 spinning velocities independently of every single propeller. And what we want to do normally, right, we want to control 4 control outputs. That means the position in X, Y, and Z. So my first 3 variables that I want to control. And the yaw heading. So in which direction is my drone looking? So these are the control outputs that I want to control. If I just have 3 control outputs left, I can just control 3 control outputs. That means I have to give up 1 control output. And what do you give up if you have position and orientation? You give up the orientation. So you can still control where is my drone, but you start to spin uncontrollably about the z-axis. And that is something you can't control then, in that case. So the solution to that is you can control the drone if one propeller breaks, but you have to land as fast as possible because you start to spin, and this will just bring your IMU out of control, and as well the control is not great.
Due to technical reasons, we have to take a quick break, but we're going to hear from Marius about university politics, and we'll be right back after this.
At time of release of this episode, the university elections are just around the corner. Just recently, the first ever printed navigator, our student council newspaper, was released, including an interview where I give all the explanations you need on the university elections. So go check that out. But here's the most important facts in short. As every year, you get to elect your representatives to the Senate, School Council, and Council of Student Representatives. In the Senate election, the top 2 candidates will take office, and in the school election, the top 4 will become the members of the School Council. They will be your most important advocates in the coming academic year who put in a lot of effort. So, as a token of your appreciation, I ask that you participate in the election. When you get the ballot for the school election, the 4 members at the top of the list are the candidates who actually want to join the school council. Everyone else will become a voting member of the Council of Student Representatives.
Welcome back, everyone. So we were talking about the topic of certifications and redundancy. Is it, let's say, more difficult than already with conventional, commercial aircraft
Yes.
in the future?
Yeah, so there's definitely just a fundamental difference. Let's just compare the closest aerial system that is working and has certification, right, compared to like a multirotor system. That's a helicopter. And a helicopter has, let's assume that the main engine fails, has the capability to still land safely just due to auto-rotation, right? So the propeller starts, or the main rotor starts to spin. That gives you sufficient thrust to still land the vehicle safely. I mean, it will be an unpleasant impact, but let's say like a skilled human pilot is able to land the vehicle safely. That is different for a quadrotor, right? So a quadrotor, I would not sit into or board a quadrotor-based human air taxi. Really, that would just not be safe enough. So if you would lose one propeller, you would start to spin uncontrollably about the yaw axis or the y axis, the upwards axis. So that would be something I would not do. You have to have additional layers of safety included. So that renders it down to always having enough propellers spinning that generate enough thrust to still land the platform. So if we take a look, for example, to one aircraft that is probably the closest to be certified for the European airspace, which is the drone from Volocopter. I'm not aware of exactly the amount of rotors they're having, but I think it's like the amount of like 16. And they have like 3 redundant systems for every single component to still keep enough propellers spinning to then, in a case of emergency, to land the platform. So there are like 3 flight controllers, 3 controllers, or speed controllers for every single motor in case that like a certain amount of propellers fail. I don't know the details about how many are allowed to fail, but a couple of rotors are allowed to fail before the platform is not controllable anymore.
And so I imagine when it comes to certifications and that topic of, that we have to deal a lot with in aerospace, it's probably a bit more difficult to get these types of projects certified than, conventional commercial aircraft. Is that case?
Yes. So to be open here, I'm not an expert on certification of aircrafts. But there has just recently been a change in the certification of this kind of new class of aerial systems. So especially electrical driven helicopters or multirotor platforms. But then the details you would have to ask someone else.
Okay, so you said you mostly focus on autonomous flight. Which applications, like what are the main applications you see for such systems?
So let's dial back there a little bit into history, right? So for multirotor platforms and for autonomous vehicles in general, right, coming from history, the main application was just taking pictures of the environment. So just have a camera on board and you take pictures. And let's say like there's a huge class of hobby pilots that offer exactly the service. So if you want to have a picture of your house or of something else, then you can just like call one of these photographers and they will immediately do that. And that is already an existing business model. So there are like thousands of quadrotor pilots and multirotor pilots that can offer this service. But if we go into more recent stages, right? So we see that these kind of platforms develop business cases in many other domains. So for example, the first one is like doing surveillance on food production, right? So just like in the farming domain, they check where are crops growing, where is more fertilizer needed. But this is still a little bit in the domain of just taking pictures with different sensors, right? So with all kind of sensors. Even more interesting, just recently more companies do like maintenance of, for example, construction sites. What do I mean by maintenance? So basically more like checking how is the construction site evolving by building high detailed 3D models of the construction site. So you get like a really almost live updated view of the construction site. But what I actually would like to see more in the future is that we really use these platforms to go into contact with the environment. So having a platform equipped with, for example, a manipulator or with like a rigid and effector that has a sensor on board to, for example, the first and easiest thing what we're already, or what some companies are trying to do is just, for example, checking the infrastructure or the mechanical integrity of bridges. So something where you would normally need to have either an industrial climber or where you need to set up lots of scaffolding to reach the object of interest from underneath. But that takes both either lots of time, right, to set up the scaffolding, or you have to put some kind of an industrial climber at risk. So we see that like in Europe, we have like plenty of accidents with industrial climbers per year. And that's something I would like to see, that this is in the future replaced by autonomous aerial systems that are really able to do exactly the same task or even more interesting task than an industrial climber is able to do to, for example, check the integrity of a bridge structure. But then let's go even further there. So on the long run, what I would like to see that we really can do tedious and challenging manipulation tasks with aerial systems. So just think about, we have like a very remote site where you want to construct something. So that might be, for example, a broadcast cell tower. This could be in the future constructed by a fleet of autonomous vehicles that really do the task fully autonomously. In one of the recent lectures were part of the Tomb Night of lectures, I just talked about whether we will see in the future like delivery services by drone. And I'm a bit skeptical about that, but it might as well in the future be a business case that we just get like delivery services done by drones. Why am I skeptical? The challenging part with drones is the scaling. Right, so to make it a proper business model, just a delivery service, you have to have hundreds or thousands of drones that do the delivery without any failure. So that it requires that there is not a human pilot behind every single drone, otherwise it's not a business model. So they have to really fly fully autonomously without a human interacting with the drone. And to make that safe, you need really lots of training, lots of experience, And that is very challenging. So you have to as well, that comes again to the case where if you drive a fleet of thousands of drones, then you always end up in some edge cases that you did not foresee. And I guess for a commercial service that is supposed to be cheap, right? The delivery has to be cheap, otherwise it will be replaced by a human. This is very challenging.
Without explicitly saying it, you were touching on the point of aerial physical interaction. And so essentially just trying to have... So first of all, how would you define aerial physical interaction?
That's easy. Aerial physical interaction happens as soon as you touch something.
Okay.
Right?
As the drone touches something.
The drone touches something.
Okay.
That might be with like a rigid component that is attached to the drone, or that might be with some kind of an end effector, like an anthropomorphic arm that you have underneath the drone. That is aerial physical interaction. So you need to touch something.
Okay. And so on that topic then, what are the main challenges of having a drone that's meant to have as its task aerial physical interactions?
That's a very good question. So if we go back again to the robotics domain, right? Robotics researchers have been very afraid of contact for a very long time. So we have a long history of trying to figure out trajectories that don't touch anything. Why is this the case? Some people consider contact as challenging. There is a truth behind it. Why is this the case? So if you think about, again, on the systems level, what makes life easy for control scientists is if you have like some kind of a change of your system, or let's phrase it differently. If you have a small change on your system, this small change causes then some small change down further the chain. But a contact is something that happens immediately. And that changes a lot of things on your platform. So it changes the dynamical model, it changes how you can control the platform. And modeling contact itself is as well challenging. So why is this the case? Especially if you think about it for a Quadrotor platform, you don't know exactly where the contact is happening. So like in the simple cases, right, where you have like a rigid robot that is maybe just a manipulator that is screwed on your table, you have lots of information about it. You know very detailed where the end effector is. You usually as well have some kind of task where you exactly know where the object is that you want to touch. So therefore you have a very well understanding of where you touch something. But if you use an aerial system, that is significantly harder, especially if you think about the domain of an autonomous contact, because you have uncertainty about the location of the drone itself, you have uncertainty about the object that you want to touch, you don't know exactly where will you touch it, and that changes significantly the challenge in the contact. And that's why we're doing it, because it's a challenging problem that has lots of unresearched fields.
Hey, Paula.
Hey, Kilian!
Seems like we got a little carried away with Professor Ryll.
I think so too. This might be a bit long.
Yeah, should we just split it up into 2 parts?
I think we should.
Send the next part out next week?
It'll be out next week.
That sounds good.